In this section 3.2, we are going to discuss a few important properties of Laplace transform. Okay, so before we proceed, please ready with your table of Laplace transform because we are going to refer to this table from time to time. All right. So the first property is the linearity property. So I'm going to discuss based on the example so that you can see clearly, okay, rather than just theoretical. Okay, so the linearity property. So if we have, for example, you want to find the Laplace transform of exponent 2t plus 2, for example. Okay, so this one can be written in a separate transform as Laplace of exponent 2t plus Laplace of 2. Okay, so you can separate into 2. So by the table of Laplace, okay, so we are going to refer directly to the table of Laplace. Okay, so the Laplace of exponent 2t, if we refer to the table, so the third one here, okay, exponent of at, then the answer would be 1 over s minus a. So since we have 2t, then the answer would be 1 over s minus 2 and Laplace of 2, so 2 is a constant. So the transform, if you refer to the table, it is the constant itself over s. So we have 2 over s. All right. So this is the first one. The same thing, if you have exponent 2t minus 2, for example, then it's going to be minus. Okay, we can separate into two terms. Okay, Laplace of exponent 2t minus of Laplace of 2. Okay, so that is the first one here. And the second one, if we have a function that is multiplied with a constant c, okay, for example, we want to find the Laplace of 2 exponent t, for example, then it can be written in the form of, okay, 2 Laplace of exponent t. Okay, so we can put aside the constant and multiply with the Laplace. Okay, then it is 2. Okay, so based on the table, it is 1 over s minus 1. So it is actually 2 over s minus 1, which can be written in that form. Okay, so that is the second one. So you can see the example here. It is written, so you can see here it is given in details. Okay, so but I would like to highlight, okay, the common mistake. Okay, so sometimes you have something like this. So the Laplace of t exponent 2t, for example. Okay, sometimes students tend to write it is equal to the Laplace of t times Laplace of exponent 2t. So this is not true. Okay, cannot be that way. You only can separate into 2 when you have plus or minus only. Okay, so like this one. Okay, if it is multiplication or division, then you cannot simply divide, okay, the multiplication to be into 2 multiplications or divisions to be, okay, if you have something like t over exponent 2t, then it is not equal to the Laplace of t over Laplace of exponent 2t. Cannot be. Okay. Let's see the second property, which is first shifting property. This is very, very important. Okay, but you don't really need to memorize the name of the property. What's important, you need to know how it works. All right. So the first shifting property says that, okay, if the Laplace transform of ft is ff, okay, so this is the well-known notation, Laplace of ft is fs, then the Laplace of exponent at times ft is fs minus a. Okay, so if we refer to the table, it is here. Okay, so this one. So this is first shifting property. Okay, if you have a function ft that is multiplied with the exponent at, then the answer would be in the form of fs minus a. So we need to find what is the equation for f, okay, s minus a here. All right. So I've stated the proof here by the definition. See, so you can pause this video a bit and go through this proving. Okay, I hope this is clear to you guys. Okay, this is just for your information. Every Laplace transform can be proved by using the definition. Okay, the first part of this chapter. Okay, in your previous video. Okay, I'm going to go straight to the example, okay, where we apply the first shifting property. Okay, example 4 here. Find the Laplace of exponent 2t times t. Okay, so this function here, the transform here, okay, we want to map to the Laplace of exponent at ft. Okay, by the table, it's supposed to be fs minus a. All right, so whenever you have a problem of Laplace transform, okay, the first thing that you need to do is to map to your table of Laplace. Okay, see which one, okay, that you need to refer. For example, for this one, you have exponent times t. Okay, so if we refer to the table, okay, on the left hand side, you find where is the exponent. Do you have exponent? Okay, so you have here, okay, exponent, and another exponent is here. Okay, so we need to refer to this one because in the problem we have exponent multiply with another term or another function. Okay, so it is actually in this form. So we need to map to this one instead of this. All right. So, all right. So in this case, okay, if we map exponent 2t times t to the exponent atft, so we know that our a is supposed to be what? 2. All right. So actually, you look here. So we have exponent 2t, you map to exponent at here. So the t here is just, okay, some function in the form of ft. Okay, all right, so a equals 2, then and then our ft is t. All right, so we know the answer at the end supposed to be in the form of s minus a. Okay, so the idea is if we can get what is fs, then we can get fs minus a. Okay, so from the ft, we can get the fs because we know the Laplace to, okay, note that the Laplace of ft, the answer is fs. Okay, the standard notation, the Laplace of ft is fs. Okay, so it means that if, okay, we find the Laplace to the t here, then it would be our fs. Okay, so by the table, okay, Laplace of t, so we need to refer to this one. The Laplace of t is, the Laplace of t power of n is n factorial over Sn plus 1. So in our case, we have t power of 1. So our n is 1. So we have, okay, here 1 factorial, which is 1 over S n plus 1. So our n is 1. So we have 1 plus 1. So s squared. Okay, so this is Fs, our Fs. But our answer is supposed to be in the form of Fs minus A. Alright, so therefore, the Laplace of exponent 2t times t, okay, which is Fs minus A, where our A is 2, then this is 1 over s minus 2 square. Alright, because we know if Fs is 1 over s square, therefore if we have f s minus apple, for example, then it's going to be 1 over s minus apple square. So similarly, if we want to get Fs minus 2, then based on our Fs, we have 1 over s minus 2. Okay, so the power, okay, follows accordingly. Alright, so that's the first example. Okay, look at the second example on the first shifting property now. Okay, so we want to find the Laplace of exponent 4t times cos t. Okay, so again, okay, we have a function cos t that is multiplied with the exponent at. Okay, so we want to map this one. Okay, map to Laplace of EAT FT. Okay, first shifting property. So the answer is Fs minus A. Okay, so we map exponent 4t and exponent 80 so that we know that our A is 4 and our ft is cos t. Alright, so based on the ft, then we need to get our fs, okay, by finding the Laplace transform to the cos t. Okay, so fs is the Laplace of ft, where our ft is cos t. Okay, so by the table, okay, so if we refer to the table, find the Laplace of cos. Okay, so here cos at, the answer is s over s square plus a square. So in our case, we have cos t, so a is 1. Okay, so s over s square plus 1 square. So go back to this one. So the answer is 1. S, okay, s over s square plus 1. Okay, but this is not our final answer because the final answer is supposed to be Fs minus A. So therefore, the Laplace of exponent 4t cos t, okay, which is Fs minus A, where we have A equals 4, so Fs minus 4. Okay, but you cannot stop here. Okay, so we need to write what is the expression for the f. Okay, so since fs is s over s squared plus 1, so fs minus 4, so basically you just substitute s with a s minus 4. So s minus 4 over s minus 4, so don't forget we need to have power of 2 here plus 1. Alright, by looking at this term Fs here. Okay, if you know your Fs, then you can find Fs minus A. Okay, s minus 4 in our case here. Alright, so that's how we use the first shifting property. Alright, so in the next video, we are going to proceed to the third property, which is the multiplication by t power of n.